When we talked about derivatives, we talked about the mean value theorem, if you guys remember doing that. Well, we have a mean value theorem that we use for integrals as well, okay? But we're going to call it the average value of a function instead, or the average value theorem. It could be considered the mean value theorem. When we do that, we're literally just taking 1 divided by b minus a, the integral from a to b of f of x dx. So we're just really going to integrate, and we're going to use that limits, the limits to help find the average or the mean value across it. So when we take a look at that, we want to find the average value of f of x equals 3x squared minus 2x on the interval 1 to 4. So for us, it's a matter of identifying what's a, what's b, and our function. So a is 1, b is 4. So when we write this integral out, we're going to get 1 divided by 4 minus 1 times the integral of 1 to 4 of 3x squared minus 2x dx. We're just going to simplify, so we end up with 1/3 in front of that integrand. Then we take the antiderivative of 3x squared minus 2x. That ends up being x cubed minus x squared. And then we evaluate that integrand from 1 to 4. So most of the time, you do the integral evaluation first, and then that coefficient, that 1/3 that's out in the front, we apply that at the end, because it has to be applied to every single part of that integrand. So always do the integral first, and any leading coefficient that you've had to factor out in front of the integral or do, you implement that at the end. So when we substitute in 4 and 1 for x, and we work through the integrand piece, we get 64 minus 16 minus 0, which is 48. So then we take that 1/3, okay, part of that average value theorem in front, so 1/3 of 48 is 16. So there's where we're using it in that scenario. Let's take another look at example 19 here. Okay, so find the example. Find the average value of f of x equals 9 minus x squared on the interval -3 to 3. And make sure that it equals its average value. Okay, this is going to be one that is very similar to one of your homework problems. So make sure that you pay attention on this one. So there's 2 steps on this one. We have to find its average value theorem, and then we have to set it equal to the original function to find what the value is. On your homework problem, okay, I'm going to give you the average value. You just need to find on one of them, I'm going to give you the average value. You need to find what the x value is. So it more applies to the second part of this problem on one of your homework problems. Okay, but for this one, we need to find the average value first, and we want to find where it equals, where the actual function equals its average value. So what we're going to do is calculate using the average value integral. So it's 1 over b minus a, integral a to b of f of x dx. For us, a is -3, b is 3. So we're going to get 1 over 3 minus -3 times the integrand of -3 to 3 of 9 minus x squared. Simplify that coefficient in front, so we end up with 1/6, the integral from -3 to 3 of 9 minus x squared dx. Keeping that 1/6 in front, we find the antiderivative of 9 minus x squared, which ends up being 9x minus x cubed divided by 3. We're going to evaluate that from -3 to 3. I'm not going to go through all the evaluation steps. You guys should be able to plug that in and get those values and follow the notes here. Keeping that 1/6 until the end, though, so you're going to have 27 minus 9 minus -27 plus 9 times that 1/6. We end up getting 6. That's the average value of the function. Now, that's not the solution to the problem yet. We're not quite done. We have to do the next part. Okay? If I asked you just to find the average value, yes, we would be done. But we want to find where the function equals its average value. So we got to take the average value, which is 6, and set it equal to the function 9 minus x squared. We're going to solve for x. When we do that, all right, simple solving, algebra, we find out that x is plus or minus the square root of 3. That is where the function actually equals its average value over that interval. Okay, so I put an asterisk on here. That's going to help with problem 14 on the homework. I believe problem 14, though, I gave you the average value. It's literally very easy setting it equal to it and solving. Okay, next we're going to get into the second fundamental theorem of calculus. Okay, for us, it's really just doing some of the same things and what it really equals. Okay, so if we take a look at the left-hand side, we have a definite integral as a number. So a to b of f of x dx, where f of x is a real function and a and b are constants. Okay, now what we're going to do over here on the right, it's the integral as a function of x. So notice what's really changing here is the integrand goes from a to x now, where x is not a constant, x is an actual variable that we're going to be applying. Not anything really complicated here, okay, but that's going to help us do some different types of integrals now that we're going to get into. It's going to be something that you might have to do in physics and things like that as well. Let's walk through it though when we look through example 20 here. Example 20, capital F of x equals the integral from 0 to x of cosine of t dt. Notice also, and I didn't mention this above, but that our function now is in a different variable. So we are in, the aspect of time anytime we use t or dt or those sort of things. So when we do this integration, we're going to have two different variables here. The integration, or the antiderivative, is going to be in terms of t, and then we're going to be substituting in x, okay, as one of our limits. So unbounded essentially in this case. So the solution, sine of t is the antiderivative of cosine of t, right? If I took the derivative of sine of t, I would get cosine of t. And we're going to evaluate that from 0 to x. So sine of x minus sine of 0. That ends up being sine of x is sine of x minus sine of 0 is actually 0. So our solution in this case is literally just sine of x. Another note, second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the integral is the function back itself. Alright, so notice that d dx means we're taking the derivative with respect to x from the integral of a to x of f of t dt. Just tells us that we're going to get f of x back. So we're going to get this function, and now instead of a function of time, it's going to be a function of x. So let's roll through that here in example 21. We're going to evaluate the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 dt. So, a couple different ways. If we look at this integral is a function of time, and we're going from 0 to x, but once we integrate this function, it'll have an x in it, but then we're going to take the derivative with respect to x. So this is kind of a simple shortcut using the second fundamental theorem of calculus. Since we are going 0 to x here, and we're going to take the derivative of x, the answer to this is literally just being able to replace this t with x. So the derivative with respect to x, if we integrate from 0 to x of a function that is in some other form of a variable, just gives us that function back only in terms of x now instead of t or v or u or whatever variable that we end up using. So in this case, the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 dt ends up just being the square root of x squared plus 1. So just some quick and easy substitutions that we can go along with there to make that a little bit simpler. We're going to continue in the next video with some more second fundamental theorem of calculus problems.